Hello, my name is Jeremy Patridge. I'm taking Geology 4155C, Spring 2020, and welcome to my presentation. So, the article that I chose is regarding the dynamic topography changes of the eastern United States since 3 million years ago. And I'm actually kind of excited that I picked this because it worked well with the research paper that I did. So, really, what was this research about? Well, traditionally, most geologists, when looking at sea level change, have used just very simple denominators to know where the maximum was of sea level rise. In one particular diagram, as we can see here, was the Orangeburg scarp. That was used most dominantly because it's just easier to use topography to see where shorelines were of ancient seas. And some of the research that came out of this was that we can't do that actually, that it's not as effective as we thought. So as we can see, a distortion of ancient shorelines and flooding surfaces along the U.S. Atlantic coastal plains are direct results of the fluctuations in topography. So topography is able to change, the landscape is able to change a lot of different ways. One in particular is going to be eustatic rebound. So just the idea of when you have ice pushing down and it popping back up, so just kind of having that push and pull factor. Another thing that they really looked at was at mantle flow and seeing how the mantle flow underneath this continent really could affect the topography. So as you can see, it says simulations of this topography change would have been global, long-term sea level change, and perhaps even climatic factors. So what they ended up doing is looking at first the sedimentary rock that was found between Virginia and Florida, and they had a very rich fossil record that also started implying that there were some differences in what we saw along different shorelines, especially during the Orangeburg Fault. So these results provided additional evidence that the mantle flow is intimately involved in the shaping of the Earth's surface, as it influences surface topography through uh, perturbations. That being said, they said there's opportunity for future work within this, but they brought in the Farallon plate. So if you're not familiar with the Farallon plate, so you have the North American plate, and then you have the Pacific plate, which that's where I am. I'm on the Pacific plate. Well, there was a third plate, a middle plate between those. It was the Farallon plate, and it was a subductive plate. And so what they were discussing is that as that material had subducted underneath the North American plate, it added additional material that could otherwise change the convective flow as far as the East Coast, which could then cause either additional increase in topography or decrease in elevation, which we'll talk about in a little bit later. This is a diagram I pulled from the article itself showing post-mid Pliocene warping and incision of coastal plains. So there's actually a three-part diagram. So A is the bigger one that's showing the relief topography. So they're using a topographic map of today and then utilizing this images of the low relief topography. The second one is looking at the elevation change based on latitude, and they found that there was a lot of correlation with that. So as you actually headed farther north of latitude, we can see that there's an increase in elevation. And then the last one down here was just looking at fluctuation change in sea level of the surface of the ocean floor. Moving forward, some of the research methods that they used a lot. They actually, just to kind of share, the last page of the article, which is all this right here, those are all other people's research that they used and other models that were done, and they were able to then compare those with their own research. So as we can see, the calculated global mantle convection of flow by using these models show that there could be a 3D rendering of the density in the mantle to understand long-term sea level changes. So the advantage of looking at these inverted 3D renderings is that it's able to show us what's happening now and a little bit in the past, but it does have a limitation as to how far back we can go. So it isn't that effective to look back 3 million years, but we're able to then look at current status of that flow and moving forward as to what to expect. Are we going to be expecting any form of rebound or uplift? Comparing joint seismic geodynamic tomography inversion, which is these gray arrows right here. So these are using stationary pieces that have already been observed, then overlying that in a layer showing a color distribution of retrodicted tomographic changes to understand landward erosion. So what ended up happening is the Orangeburg Scarp has been used as really a shoreline for many, many studies of saying that during the last glacial maxima, where were shorelines? Because at that point we know that during the glacial maxima, that part of North America got pushed down, and then looking at maximum sea level rise, what was that correlation? And so this line has been used mostly as that because the geology is very different on either side. But what they've come to find out is that it's not a very good line to use because up in this area up here, there was a tremendous amount of fluvial morphology, a lot of drainage that occurred and has actually weathered and removed a lot of it, of the material. So anyway, looking back at the scarp, we can see that we've got these different fault zones that they were looking at, these seismic geodynamic tomographies, and then overlying it with this colored scheme, the schematic, which is used to show a topographic change dating 3 million years. So then they were able to correlate sea level changes based on global events such as the collapse of Greenland and the Antarctic ice sheets. Um, that being said, by doing the math and saying, well, wait a minute, if we kind of ignore this scarp zone and just look at the volume of ice that could have been and would have been put into the ocean, the water at that point would have melted, where would those lines have been? And they actually found that this line better represents beyond their research area, being closer to the 4 million mark. So that being said, that most geologists, as we'll discuss later, use this as a boundary line to show um, sea level rise maxima, but that's actually not an appropriate line to use. So that being said, within the research methods, during the rotation adjustments of the Earth, which are essentially the Milankovitch cycles, there's 3 different cycles. There's precession, there's eccentricity, and then there is precession, eccentricity, and I can't think of the third one. My brain just blanked out. But anyway, these are mathematically calculated glaciation cycles, and so our last major glaciation, maximum glaciation, was the Laurentide ice complex, and part of the research methods were to study how far did the ice advance, and then that being said, because of that advancement, where was the bulge on the landscape? And they found that a majority of the bulge was actually located down in this eastern part of the U.S. by Florida. So what does that bulge mean? Imagine if you had a plastic globe, and like those blow up ones, and then you put your hands on it and you're going down North America and pushing down, pushing down. We would find that there would be a portion at this point, you kind of see a little bit here, that during that glacial maxima that it actually dunked Florida under the ocean a little bit. But in that process of dunking the southern part of Florida, there was a bulge that would create as well. And that's what they're talking about. The peripheral bulge of the Laurentide ice complex was located mostly on the east coast, and has continued to subside since the last glacial maxima. So that bulge, it was created by pushing the rubber down on the globe in that sense. So you have a down part, and there's still a little bit of a bulge that creates. It's still subsiding. It's taking a long time to rebound from that advancement. So they used all of this data, again, looking at different stationary pieces, looking at the topography, looking at the tomography, looking also at the convective flow. That brings us into some of the results. So the results imply that the east coast of the U.S. has an extremely dynamic topography, and kind of to a lesser extent, glacial isostatic adjustment accounts for the current architecture of the coastal plain and proximal shelf. So what does that mean? Well, I think that most people assume that California and the West Coast has had a tremendous amount of dynamics when it comes to topography, but I think that this is kind of bringing in the idea that the east coast of the U.S. has undergone a very different type of dynamics. That being said, looking at not just the glacial isostatic adjustments, so just those push-pull factors I mentioned earlier with ice advancements and retreats, but also looking at some of the underlying morphology, looking specifically at the push and pull factors through faulting, as mentioned a few diagrams ago, and seeing how the molten magma underneath the earth and how that convective current's working, how does that play a role on this as well? Taking into consideration the fact that we do have a continental shelf that wraps around. Additional results confounds earlier attempts to use regional stratigraphic relations as the reference for longer term sea level determinations. So that just means is that we can't just walk out and just look at the landscape and go, okay, well, based on how the landscape looks now, that this is, and we can see that there's a shoreline, that must have been where the water maxima was. And what the reason I'm saying that is because most of the research that was resulted from this was saying that it's not stationary, it's not a straight line, that it is dynamic, that there's some areas that have as much as a 60-meter plus or minus 15-meter change in a standard deviation of up and down in topographical change. So there's been a lot of erosion, there's been a lot of manipulation to the landscape, so it's not very clear as to where that singular line should be drawn. In that knowing that the boundary and the design of the East Coast that we have today is not what it would look like 10,000, 20,000, even 3 million years ago. And that we have to make those adjustments when learning about, well, I think the biggest example that I can give you that I kind of pulled from this is that there's a website where you can literally add, it's the bathtub theory, right? Where you can add additional water to your bathtub, or add additional water to the oceans, and that it should just go up evenly on all around it. And it doesn't work that way, because if the continent itself had a different type of topography at the time of its maxima, then it would look very different. It would be very different in that sense. So that being said, so there was a lot of interesting pieces to that. So this is what they used. This is that paleogeography of the coastal plains. This is what they have now projected that the shoreline of the East Coast would have looked like. So as you can see, this is that Orangeburg Scarp. That is not the boundary. That the boundary is actually down here. These would have been your beach faces at the 3 million year mark. And so again, a lot of change has occurred in the last 3 million years. So what are those implications for Florida? Well, it has been interpreted that the Orangeburg Scarp is not the marker of sea level maxima for the Pliocene, rather that of a marginal sea level 3 to 4 million years ago. Much discussion has been said about sea level increase due to the current warming trends and advancing melting ice. So historical data can now prove where the sea level margins were some 3 million years ago, but now to understand the present surface shows warping of up to 60 meters. So it is much more difficult to predict oceanic shorelines, knowing how dynamic the changes have been and then will be in the future. So what I'm saying there essentially is that we can definitely take the topography of the East Coast and predict sea level increase where it will, and then where will those sea levels rise and limit themselves to. But as the landscape continues to change, if we're trying to project a model of maybe 10 meters in 1 million years, the landscape will be very different in 1 million years, so it won't be a very good predictive model. So the summary, well, in summary, the topography along the eastern U.S. has changed dramatically. There's no doubt about that. Using retro-dicted paleogeography at the 3 million year mark, it definitely matched that of the mid-Pliocene marine strata found in the Albemarle and southern Salisbury embayments. With the use of model mantle convection, it is suggested that the mantle has greatly influenced the topography along the eastern United States, thus affecting shoreline deposits. Uh, that being said, they mention lightly, but the fact that further research does need to be done to understand predictive sea level increase and Florida's current shorelines, as inferences of Pliocene global sea level heights or stability of Antarctic ice sheets cannot be deciphered in the absence of an appropriate mantle dynamic reference frame. So again, understanding the dynamics of our lower mantle and our uppermost mantle, and how that can drive the direction in which our plates are moving, and driving really just tectonics altogether, and then looking at topographic uplift. There's just so many elements at hand that I think that this paper was able to report certain things that were fact, and saying that maybe we need to look at things a little bit differently, but it was also able to say that there's a lot more that we don't understand, and so it makes it very difficult to predict in the future if there's still kind of some of those missing gaps, that it's not as easy as we thought, because certainly we can use the fossil record to understand and to date that, but at the same time we also know that because of erosion, especially in certain parts of the US where it happens more predominantly, especially dealing with the type of underlying geology, it becomes harder to fill in those missing links. All right, and so then for my bibliography, there we go. I've got the paper that I looked here, and this is actually the image that I wanted to show, um, the map showing the advancement of the Laurentide ice sheet. So anyway, I hope you enjoyed, and I hope that you learned something here. And cool. Thank you.